Good morning, everyone. Thank you, Tonya, for the kind introduction. I will go through thrombotic microangiopathy. This is my disclosure. Um, I'm sorry. Oh, yeah. So basically, just for the people who don't know what is thrombotic microangiopathy, it's a group of rare disease affecting the kidney or different organs, such as the brain, the heart, and as a nephrologist, we are involved in the kidney parts. All these diseases are sharing biological manifestations, such as hemolytic anemia, thrombocytopenia, and there is a myriad of causes of thrombotic microangiopathy at different diagnoses. In any case, it's a medical emergency, and the early detection of this disease is very important for the clinical management to prevent organ loss or patient death. So, for the a clinician, is basically a complex a nightmare to manage at the very beginning those patients, even though we identified TMAs. It took at least 3 days to screen up the different subset and different diagnoses. It's very complex. At the very end, sometimes we are, the question is when to start a genetic test to pinpoint the different entities associated with genetic disorders in the group of TMAs. And a specific subset is complement-related disorder associated with TMAs, and we do have a dysregulation of the alternative pathway of complement with complement inhibitory proteins such complement factor H, CFH, complement factor I, CD36, which are some defects lead to overactivation, and basically the terminal pathway of complement is overactivated. And we do have treatment such eculizumab or other blocker that could regulate the genetic defect. So at the end, the overactivation of the complement system leads to glomerular thrombi or arterial thrombi, like exemplified here. And the question is to start a treatment for limit the danger of the overactivation. And one of the specific genes, complement factor H, is a very complex, very complex locus. And we have related genes, CFHR3 to 5s, which are not pseudogene but real true genes, and it's a very complex region to decipher as a biologist. And so there is hybrid gene formation leading to loss of function of complement factor H or antagonistic effect of wild-type CFH. Basically, it's a phenocopy of complement factor H defect. And we are not to be confused with the real common deletion of complement factor 1 and 3, which are very common. Nevertheless, those alterations which are common are associated with complement factor H antibody generation. So this is just a cartoon of the very similarity of complement factor H and complement factor 1. And those the differences and hybrid gene are just could be detected by MLPA and not detected by short-read sequencing, NGS classic technology. But we can, spoiler alert, we can detect all those alterations with nanopore sequencing with specific algorithm. So we do have treatment for this disease, complement factor H defect, complement factor H, CD46, and so forth. Very powerful treatment that changed the fate of the disease since 2013. And just to sum up, there are other related genetic defects associated with TMAs. We are those response to eculizumab and other phenocopies such as irritated glomerulopathies that are more common but could mimic TMA entry point at the clinical level. So we have to decipher all these forms of genetic defect to give the right treatment at the right time for the patient. So last year we published a position paper out on more turnaround time of 3 weeks using short-read sequencing. And now I will show you what we are moving on from 3 weeks basically to 2-3 days with nanopore sequencing. It could save money. We can have the right treatment at the right place, at the right moment. And so the right treatment at the right time with a molecular proof. This is the motto we have to envision. So this is the algorithm. It's more simpler when you add up on the end a genetic test, a fast-track genomic test. And next, we are using adaptive sampling with nanopore sequencing moving from 3 weeks to 3 years, as I said, and we are screening for 100 genes with 2% gene of comm, so different diagnoses from different nephropathologies far beyond than the TMAs itself. So at the very beginning, we use million floor cells with a good sensitivity and recall in 10 patients with each screen, but we cannot, we just can rule out a diagnosis, not firmly confirm a diagnosis given the low coverage we reach with a million floor cells. And now with Promethean floor cells, 4 hours on our bench, 24 hours of sequencing on a Promethean floor cells, and 8 hours of bioinformatic analysis, we reach a very high sensitivity and recall comparing to the clinical exome test we are doing at the same time for those patients. And so in May 24, I can say we have a very accurate test, and we can detect as well CFH hybrid gene that is not affordable with short-read sequencing at the same time in less than 3 days. So this is one of the representation of very complex rearrangement at the CFH locus. We can detect those patterns with specific pipeline in partnership with sequence genomics, and thus we push the limit of detection of variant pattern far beyond that the short-read sequencing could afford today. So this is just a bench. It's quite messy, but still we increase the quantity of data per 5. The coverage beyond 80x at the target for TMA gene. For example, we can do phasing, methylation, and other things that are very important for differential diagnosis of different TMA phenocopies, as we can cover different genes associated with TMAs and other nephropathy as well at the same times. So this is a representation of the different paths we did use in the last couple of years using Oxford Nanopore sequencing in TMAs. And so at the beginning, we are 72 hours analysis time. Now we are more on 48 hours analysis. And we do have external computing power to solve different complexity for hybrid gene, for example. We do not observe a difference in ACT versus SUP for SNV and CNV detection, but for hybrid gene detection, we need SUP to be optimal at that setting. So we use a tertiary analysis with sequence genomics, which use an AI to pinpoint, for example, the CFH version on the top, on the first of the list, very easily for the biologist and the clinician that could discuss together around the patient. So this is an example of the paper we have submitting currently. This is the 3 positive diagnoses that change the life of the patient. A turnaround time on 266 days with a whole exome sequence in short read, and a fast turnaround time less than 5 days in the rest, and you can see a significant time frame to save actionable action for the patient. And so I will end up my presentation with 2 stories, very recent story in April. First is a patient 24. It's a 40-year-old man with malignant hypertension. He started operation at 28, and he ended up in our medical area with an acute kidney injury, anuria, malignant hypertension, and a molecular diagnosis analysis was provided in 44 hours. We can start eculizumab, and he will recover of his disease. Later on, the diagnosis will confirm by short-read sequencing, by exome sequencing. And patient 25 is a 32-year-old woman with Crohn's disease, with acute kidney injury and anuria and thrombotic microangiopathy. The renal biopsy shows focal segmental glomerulosclerosis, non-specific lesion, and TMA lesion as well. And the molecular diagnosis could provide in 40 hours. And the diagnosis was not a TMA-related gene, it was TTC21B. It's a nephronoptosis genes that could mimic and phenocopize TMA phenotype as it published. And so we avoid to give eculizumab. And so at the end, when we cumulate all the tests we did in 25 patients, the estimated cost we save, the money we save doing this early on in this screening is 500,000 euro at least, because we don't give eculizumab as expensive treatment different patients, because we are now a molecular proof entities. So I think I try to convince you that fast genomic for TMA is feasible. It can drive actionable diagnostic for life-changing therapies for the patient. And I think that the motto could the sooner the better for the patient with Nanopore. I have to say that, okay? So many thanks to my dear colleague in Paris, at Sorbonne University, and my colleague from Orphan Biomics and Nanopore and Sequence Genomics. And glad to my colleague on the National Center for TMA as well. Thank you for your attention.